Section 24 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Ralt Wheeler. Geology, Chapter 13. Historical Geology, Part 1. While the life history of organisms is truly biology, and the life history of extinct forms of animals belongs largely to paleontology, yet the geologist has an intimate relation to both, to the life history of present organisms because of their effects upon the Earth's surface, and to the relics of past organic life, because their presence in certain rocks reveals the conditions that prevailed when those rocks were laid down. Historical geology, says Geikie, deals with fossils or organic remains preserved in natural deposits and endeavors to gather from them information as to the history of the globe and its inhabitants. The term fossil, meaning literally anything dug up, was formerly applied indiscriminately to any mineral substance taken out of the Earth's crust, whether organized or not. Ordinary minerals and rocks were thus included as fossils. For many years, however, the meaning of the word has been so restricted as to include only the remains or traces of plants and animals preserved in any natural formation, whether hard rock or loose superficial deposit. The idea of antiquity or relative date is not necessarily involved in this conception of the term. Thus the bones of a sheep buried under gravel and silt by a modern flood, and the obscure crystalline traces of a coral in ancient masses of limestone are equally fossils. Nor has the term fossil any limitation as to its organic grade. It includes not merely the remains of organisms, but also whatever was directly connected with or produced by these organisms. Thus the resin which exuded from trees of long perished forests is as much a fossil as any portion of the stem, leaves, flowers, or fruit, and in some respects is even more valuable to the geologist than more determinable remains of its parent trees, because it has often preserved in admirable perfection the insects which flitted about in the woodlands. The burrows or trails of a worm in sandstone or shale claim recognition as fossils, and indeed are commonly the only indications to be met with of the existence of annelid life among old geological formations. The droppings, coprolites, of fishes and reptiles are excellent fossils, and tell their tale as to the presence and food of vertebrate life in ancient waters. The little agglutinated cases of the caddis worm remain as fossils in formations from which perchance most other traces of life may have passed away. Nay, the very handiwork of man, when preserved in any natural manner, is entitled to rank among fossils, as where his flint implements have been dropped into the prehistoric gravels of river valleys, or where his canoes have been buried in the silt of lake bottoms. The term fossil, moreover, suffers no restriction as to the condition or state of preservation of any organism. In some rare instances, the very flesh, skin, and hair of a mammal have been preserved for thousands of years, as in the case of mammoth carcasses entombed in the frozen mud cliffs of Siberia. Generally, all or most of the original animal matter has disappeared, and the organism has been more or less completely mineralized or petrified. It often happens that the whole organism has decayed, and a mere cast in amorphous mineral matter, as sand, clay, ironstone, silica, or limestone, remains. Yet all these variations must be comprised in the comprehensive term fossil. The conditions of the preservation of fossils, says Scott, are much more favorable to some kinds of organisms than to others. It is only under the rarest circumstances that soft gelatinous animals, which, like jellyfish, have no hard parts, can leave traces in the rocks. The vast majority of fossilized animals are those which have hard shells, scales, teeth, or bones, and of plants, those which contains a sufficient amount of woody tissue. Again, the conditions under which organisms live have a great influence upon the chances of their preservation as fossils. Land animals and plants are much less favorably situated than are aquatic forms, and since the greater number of sedimentary rocks were laid down in the sea, marine organisms are much more common as fossils than are those of fresh water. On land, fossils have been preserved, sometimes in astonishing numbers, under wind-made accumulations of sand, dust, or volcanic ash, and in the floodplain deposits of rivers. Peat bogs are excellent places for fossilization, and the coal seams have yielded great numbers of fossils, principally of plants. The remains of land animals and plants, especially of the latter, are sometimes swept out to the sea, sink to the bottom, and are there covered up and preserved in the deposits. But such occurrences are relatively uncommon. Small lakes offer more favorable conditions for the preservation of terrestrial organisms. Surrounding trees drop their leaves, flowers, and fruit upon the mud flats. Insects fall into the quiet waters, while quadrupeds are mired in mud or quicksand and soon buried out of sight. Flooded streams bring in quantities of vegetable debris, together with the carcasses of land animals drowned by the sudden rise of the flood. The great series of freshwater and volcanic ash deposits, which for long ages were formed in various parts of our West, have proved to be a marvelous museum of the land and freshwater life of that region. On the fine-grained shales are preserved innumerable insects and fishes, with multitudes of leaves, many fruits, and occasionally flowers, while in the sands, clays, and tufts are entombed the bones of the reptiles, mammals, and more rarely, birds of the land, mingled with those of the crocodiles, turtles, and fishes that lived in the water. Similar deposits are known in other continents. But it is on the seabed that the conditions are most favorable to the preservation of the greatest number and variety of fossils. Among the littoral deposits ground by the ceaseless action of the surf, fossils are not likely to be abundant or well preserved, but in quieter and deeper waters, vast numbers of dead shells and the like accumulate and are buried in sediments. A geological chronology, says Scott again, is constructed by carefully determining, first of all, the order of superposition of the stratified rocks, and next by learning the fossils characteristic of each group of strata. To many it has seemed that this is reasoning in a circle, but that is because the argument is not fully stated, some of its steps being omitted. The order of succession among the fossils is determined from the order of superposition of the strata in which they occur. When that succession has been thus established, it may be employed as a general standard. Great physical events, such as the upheaval of mountain ranges, widespread transgressions of the sea, and changes of climate, often provide a means of correlating the strata of different continents with greater precision than can be done with the aid of fossils only. The latter are, however, indispensable means of first determining which of these events are comparable in different regions. The history is recorded partly in the nature and structure of the rocks, partly in the fossils, and partly in the topographical forms of the land and the courses of the streams. By combining these different lines of evidence, local histories are constructed for each region, until from these the story of the whole continent may be compiled. The comparative study of the fossils then gives the clue for uniting the history of the different continents into the history of the earth. The method of making the divisions and subdivisions of geological time is not yet a fixed one, and there is much difference in the usage of various writers. The names of the divisions also have been given at various times and in many lands, according to no particular system. Most of these names have been taken from the locality or district where the rocks in question were first studied or are most typically displayed, as Devonian from Devonshire, Jurassic from the Jura Mountains. Some are named from a characteristic or prevalent kind of rock, such as Cretaceous, Latin Creta or chalk, and Carboniferous. Of late, there has been a tendency toward a more uniform method of nomenclature and to the use of one set of terms for the divisions of time and another and corresponding set for the divisions of the strata. The following table represents the divisions of the scale of time and the scale of rocks which have been adopted by the International Geological Congress. Time scale: era, period, epoch, age. Rock scale: group, system, series, stage, substage, zone. It will be observed that the subdivision is carried farther in the scale of rocks than in that of time, because of the generally local character of these minor subdivisions. The names employed are, as yet, the same for both scales, and we speak of the Paleozoic era, or group, and of the Silurian period, or system. It has been proposed to give separate names to the divisions of the two scales, and this would be an improvement in some respects. Table of major geological divisions. Cenozoic era, Quaternary period, Tertiary period. Mesozoic era, Cretaceous period, Jurassic period, Triassic period. Paleozoic era, Permian period, Carboniferous period, Devonian period, Silurian period, Ordovician period, Cambrian period. Precambrian eras, Algonquian period, Archean period. Tracing the history of mankind back to very ancient times, records become more and more scanty and less intelligible, until history fades into myth and tradition. Of a still earlier age, there is not even a tradition. It is prehistoric. Similarly, among the geological records, the earliest are in a state of such excessive confusion that they are exceedingly difficult to understand, and between different observers there are radical differences of opinion both as to the facts and as to their interpretation. Furthermore, there must have been an inconceivably long time earlier than the most ancient recorded periods, as to which conjecture and inference are the only resource. In these difficult straits, astronomy offers valuable assistance to the baffled geologist. The nebular hypothesis is a scheme of the development of the solar system which is generally accepted by astronomers in some form as essentially true. The term nebular hypothesis is usually, though not with exactness, limited to one particular form, according to which the place of the present solar system was originally occupied by a vast rotating nebula, a mass of intensely heated vapor, or possibly clouds of meteorites, extending beyond the orbit of the outermost planet. As the nebula cooled by radiation, it contracted, leaving behind it successive rings, like those of the planet Saturn, but on a vastly larger scale. The rings kept up the rotation imparted by the nebula, and all of them lay in nearly the same plane. Unequal contraction in various parts of each revolving ring caused it to break up and gather by mutual attraction into masses. If these rings were composed of relatively small solid masses, like meteorites, or if they had solidified by condensation of the vapors, the heat generated by the collision, as the broken ring was gathered into a mass, would suffice to raise the temperature and liquefy or vaporize the mass. By revolution, the nebulous masses would assume a spheroid shape and become planets. The central mass of the original nebula forms the Sun, which is still in its intensely heated, incandescent state. Another form of the nebular hypothesis, called for the sake of distinction the planetesimal hypothesis, has recently been proposed by Professor Chamberlain. This postulates, as the beginning of the solar system, a spiral nebula, and that the matter of this parent nebula was in a finely divided solid or liquid state before aggregation. It regards the knots of the nebula as the nuclei of the future planets, and the nebulous haze as matter to be added to these nuclei to form the planets. It assumes that both the knots and the particles of the nebulous haze moved about the central mass in elliptical orbits of considerable but not excessive eccentricity. It deduces a relatively slow growth of the Earth, with a rising internal temperature developed in the central parts and creeping outward. From the strictly geological standpoint, the most important difference between the nebular and the planetesimal hypotheses is that, according to the former, the Earth has passed through a gaseous and a molten stage, and therefore must have formed a crust by solidification, while the latter leads to the conclusion that the Earth has been solid from the beginning and consequently never formed a crust of solidification. It is unfortunate, says W. B. Scott in his Introduction to Geology, Macmillan Company, that an account of historical geology should begin with the most difficult and obscure part of the subject, but the treatment must be in accordance with the chronological order, and the oldest rocks are the least intelligible. The ordinary criteria of the historical method, namely the stratigraphical succession and comparison of fossils, fail us here almost entirely, and the only way of correlating the rocks of different regions and continents is by means of the characters of the rocks themselves. In the present state of knowledge, lithological similarity is not a safe guide. So many metamorphic rocks, once referred to the Archean, have proved to be of much later date, that some cautious geologists, who have no confidence in lithological similarities, prefer not to use the term Archean at all, but to employ local terms for the oldest crystalline rocks exposed in a given district. The Archean includes the most ancient rocks, often spoken of as the basement or basal complex. Its antiquity is best assured in regions where it is separated by thick series of sedimentary or metamorphic rocks from the lower Cambrian, which can be certainly identified by its fossils. The Archean is composed of completely crystalline rocks of various types, massive rocks such as granite and basic eruptives, and foliated rocks like gneissoid granite, gneiss, and many varieties of schists are intermingled in the most intricate way, a characteristic well expressed in the oft-used phrase of the basal or fundamental complex for the Archean. The component mineral particles show plainly the intense dynamic metamorphism to which they have been subjected in their extremely complex arrangement and in their laminated and crushed condition. The rocks thus referred to the Archean are not necessarily all of the same age, but they are all of vast antiquity and older than any other known series. They are of very great but unknown thickness, for the bottom of them is nowhere to be seen, and even when thrown up into mountain ranges, erosion has in no case cut so deeply into these rocks as to expose anything different below them. The origin of the Archean rocks, Scott resumes, is a problem which has given rise to a great deal of discussion, but a solution appears to be near. Independently, in many countries, observers have reached the conclusion that these rocks are divisible into two great series, a schist series composed chiefly of highly metamorphosed sedimentary and volcanic rocks, and a gneissoid granite series, which is intrusive and later than the former. Assuming that this conclusion is true, at least as a working hypothesis, it involves certain curious consequences. Surface lava flows and volcanic tuffs, and still more sedimentary rocks, necessarily imply a solid floor upon which they were laid, but of this floor not a trace has anywhere been found. The question immediately arises, what has become of it? No answer to this question can yet be given, but apparently the most likely suggestion is that the ascending floods of molten magma, which gave rise to the gneissoid granites, must have melted and assimilated it. If this were only a local phenomenon, there would be nothing very surprising about it, but it would seem to be true of the entire globe, and this is a startling conclusion. It would appear then that a solid crust, however formed, was for a very long time sufficiently rigid and stable to allow a great thickness of sedimentary and volcanic rocks to be accumulated upon it, and then was engulfed and destroyed by a universally ascending magma, though it is not necessary to suppose that this took place simultaneously over the whole earth, or even within a relatively short period of time. It may have required ages in the accomplishment. Furthermore, it must not be forgotten that remnants of the floor may yet be discovered in little known regions. If this complete and universal assimilation actually took place, it is an absolutely unique phenomenon in the recorded history of the earth, though something more or less similar may have happened many times before that record began. The present writer is not entirely in agreement with Professor Scott as to the following division of geologic time, but in view of the fact that the sequence used in this summary is taken from his Introduction to Geology, no change will be made in the order of presentation. The Algonkian is the name proposed by the United States Geological Survey for the great series of sedimentary and metamorphic rocks which lie between the basal Archean complex and the oldest Paleozoic strata. It is but little used outside of this country and is not universally employed even here, but it is beginning to make its way in Europe and serves a useful, though possibly a temporary, purpose. While it is possible, though not very likely, that more advanced knowledge may make it possible to distribute these rocks partly into the Archean and partly into the Paleozoic, yet for the present at least it is better to form a separate grand division for them. The Algonkian rocks, which are widely distributed in North America, form an immensely thick mass of strata and of metamorphic rocks, which are believed to represent those strata in other regions. These metamorphic rocks were long generally referred to as the Huronian, which was regarded as the upper portion of the Archean, but, so far as can be learned, they occupy the same stratigraphical position as certain little changed sediments between the fundamental complex below and the Cambrian above. At the base of the magnificent section exposed in the Grand Canyon of the Colorado is a very thick mass of strata, separated by great unconformities from the Archean gneiss below and from the overlying Cambrian. This mass is again subdivided by minor unconformities into three series. The lower series, at least 1,000 feet thick, and perhaps more, is made up of stratified quartzites and semicrystalline schists cut by intrusive granite. Above this come nearly 7,000 feet of sandstones with included lava sheets, and at the top more than 5,000 feet of shales and limestones, in which a few fossils have been found. The two upper series are not at all metamorphic. All these strata are steeply inclined, and upon their truncated edges rests the sandstone referred to by Mr. Walcott to the Middle Cambrian. End of section 24.